Right, so for exercise 10, I'm actually going to show you how to compute the square root of x using numerical methods, but I'm going to use um, three different techniques to do this. And those techniques are exhaustive enumeration, bisection, and the Newton-Raphson approach, which will each one of those techniques will work successively more quickly or in the fewer iterations. And I like this example, and the book talks a lot about these techniques because there are often more than one way, or there's often more than one way to solve a problem writing a program. And even, many times when we use the exact same procedure, we still come up with different code. Different people will write different code. But here's a situation where you can actually choose radically different procedures and we'll get the right answer, but a lot of times as computer scientists we're not only thinking about the right answer from a mathematical perspective or a technical perspective, but we also want to try to do it in the fewest amount of steps. So this exercise uses looping and the logic that we've been developing, but it also allows us to see how maybe choosing different techniques can significantly affect the runtime and the accuracy of our solutions. So in this video, I'm going to do exhaustive enumeration, and then in the next two, so it's kind of a three-parter, I'll show you how to use bisection and a Newton-Raphson approach as well. But we'll start off with the sort of, at least conceptually, the simplest one, which is exhaustive enumeration. And if you remember from exercise 7, we used exhaustive enumeration to find perfect cube roots. So if the user typed in 27, we were able to find the fact that 3 cubed was equal to 27. Now, that program was fairly simple because of the big caveat that it had to be a perfect cube root. We're not going to talk about perfect square roots here. So we're not going to say, well, we can't calculate the square root of anything but 81 or 9, 3 times 3. Here we're gonna allow the user to type in any real number, any floating point number, and we're going to attempt to find the square root, whether it contains fractions or not. We won't deal with negative numbers or something like that, but we'll deal with non-integers. But we're still going to take the similar approach. So let's kind of review a little bit about exhaustive enumeration. So we're taking advantage of this idea of a number line. So 0 all the way through, and let's say 20. All right, so here we've got 10, 15, 5. This is the 2.5 mark, the 7.5 mark, right? And we can keep kind of dividing in half. Right, and if we try to figure out what the square root of, let's say, what's the square root of 16? Okay, well, we can establish, we can figure out whether any given number on the number line is indeed the square root of 16, right? And we can kind of move forward, and we'd hit 1 and 2 and 3, and we'd hit 4, and we'd realize that 4 squared is equal to 16, and we'd say, okay, got it. But we never really talked about increments. How many numbers are we going to test between 0 and 4 on our way to getting to 4? And the reason why that really makes a difference is, what if we're trying to figure out the square root of, let's say, 15 instead? Well, the square root of 15 is not an integer. It's certainly, so the square root of 15 is certainly less than 4. We know that because 4 squared is 16, right? But how much less, right? We don't really know. It's somewhere out here. Clearly, we're not going to be able to just kind of hop along the integers, right? We're not going to be able to just pick integers to find this. We're going to have to pick some other step. Right? We're going to have to test lots and lots and lots of values until we get there. And even then, whatever the increment is, if the square root is somewhere in between our increments, we're not going to be able to find that square root. And by the way, something like the square root of 2 doesn't have an exact number at all, right? So we're never going to find the exact square root of 2. So we need extra variables, right? We need to define a step, and we need to also define what's called epsilon, which is our error tolerance. What do I mean by error tolerance? If I'm going to try to find the square root of 15, if x squared is within epsilon, then it counts, right? So we'll say, okay, well, I might get an x squared value that if I squared x, it's not exactly 15. Maybe it's something like 14.998, but that might be good enough, right? If our epsilon value is 0.0001, for instance, well, that's within that tolerance. If our epsilon value, or I'm sorry, if our epsilon value is, scratch that, if our epsilon value is something like that, right? But if our epsilon value was even smaller, right? If our epsilon value was out here, and I said I want it to be, I'm only going to accept something whose square is 14.9999, right? Then maybe I don't have it, right? So epsilon and step are actually going to be related to each other somewhat, right? Because if I don't step in small enough increments, I might not be able to find the number that's within the error tolerance that I'm looking for. So these are all parameters into our sort of solution, and epsilon being sort of the key one. How much error tolerance am I willing to deal with? I can generally step is defined based on epsilon. All right, so if epsilon is 0.001, then maybe I'd step in 0.00001 or something like that. Otherwise, because I have this custom epsilon value and this custom step, aside from that, this is very similar to finding the cube root. I'm going to exhaustively look at every single number on the number line until I find it, or I go past some maximum value. And so we need to think about, how do I find that maximum value? So if we're thinking about where when should I actually stop? Let's kind of backtrack here. I want to clear out this pad. Let's look at an example. And the idea is that maybe we've defined the step, and I'm not going to put exact numbers to this, but maybe our step is something like this, right? So we're checking values here. All right, and let's say, and that seems like an awfully big step, but let's say the actual square root of the number we're looking for. Maybe we're trying to find the square root of 15 again, right? So the square root of 15. If the actual square root is here, and this distance is greater than epsilon, right? So this distance and that distance is both greater than epsilon. We're going to essentially miss the square root, right? We're not going to be able to calculate the square root effectively because we're going to measure here whether this value squared is within epsilon of 15 and this value squared is within epsilon of 15. And the answer is going to be no to both, let's say. All right, so we skip over. And the question is, well, how do we know when to stop? We know that, if we were to evaluate a position somewhere here, we'd know to stop because it's within epsilon. But what if we skip? All right. And the question, the answer to this question is, what's the maximum value? If we knew nothing really about the square root, what's the maximum value we could expect? And conservatively, if we didn't want to spend any time really thinking about what's the theoretical maximum value, we could just say it's x, right? We know that the square root of 15 has got to be less than 15. That makes some numeric sense, right? And so we're going to go by that, right? So if I was to kind of get unlucky and miss the square root of 15, my algorithm would keep bouncing along and it would check, and then eventually it would check a value over here. And once that was the case, once x or the value that I'm checking becomes greater than 15, I'll stop. So I actually have two stop conditions. One where I find a value that is within epsilon, and one where I kind of blow past the actual answer. The answer lied somewhere in here, but we missed it because maybe we didn't have a small enough epsilon. Okay, so let's code that up. We've got a square root of a value that we need to get the square root of. So let's calculate. Let's ask the user for that. And I'm going to have an epsilon value, and we can really choose anything. I'm going to choose 0.001. That's a pretty low value. So as long as I can find a number who, when it's squared, is within 0.001 of x, I'm going to count it as a possible solution. My step, and I'm going to base it off of epsilon. I'm going to do it epsilon squared. You might think, well, wait a second, why is step bigger than epsilon? Remember, epsilon is less than 1, so 0.001 squared is 0.00001. So it's a very small increment. And now I'm just going to loop. So I'm gonna assume that the answer starts at 0. Basically, I'm mimicking exactly what I've done here. I start at 0. And I'm going to say, well, I've got two stop conditions. While the answer squared, and I'm going to do an ABS here, absolute value of the answer squared minus x. So I don't care whether it's bigger than x or less than x. If it's within epsilon, I'll stop. So keep going while that value, answer times answer minus x, all right, while my value squared is the difference between my value squared and x is greater than my tolerance. But I have a second condition. I also want to keep going as long as the answer is less than or equal to x. If the answer becomes greater than x, then that's this situation, right? Where I missed the actual square root and now I'll keep going and eventually I cross over to x. So that's kind of like my boundary condition. Once I test a value that's past x, I know that I can't find it. And it's not that the square root of 15 doesn't exist. It means basically my step was too small. So while both of those conditions are true, I'm going to increment by the step. So I haven't found the answer yet. And when I'm all done, I have to check, did I actually get the answer? So maybe the last answer that I calculated caused this condition to be false, right? If that's the case, that means answer squared minus x is less than epsilon, or less than or equal to epsilon. It means I have a result. So if ABS of answer squared minus x is less than or equal to epsilon, then print square root of x is answer. Otherwise, I didn't stop because of this, I stopped because of this, meaning I was not able to find it with an exhaustive enumeration. And again, exhaustive enumeration, unlike other trials that will, or unlike other algorithms that we will see, it is possible that we will not be able to find the value within a certain epsilon. We lack precision. Our precision is limited by our step. And of course, we could reduce the steps to get a better result. So let's actually the first time well, I'll leave it right now, but we could play with that step and see that it'll really have an effect on what results we can actually get. Okay, so let's run this program, and let's first start with easy ones, right? So what's the square root of 16? And you can see it's taking quite a bit of time, and it comes out with 3.999. And of course, we know that the answer is exactly 4, right? But notice that our epsilon value is 0.001, and we're within 0.001 of the actual answer, right? So this is acceptable. This is that it's not. This is an acceptable range. If I was to make epsilon larger, I could still do this, but this is going to take an enormous amount of time. And it's because I'm incrementing so smallly. There's so many numbers between 0 and 16 that I'd have to actually look at and examine. So it's going to take me far longer to find this value. Rather than wait, we can kind of get an idea of just how many iterations. Let's move epsilon back to this, and let's count iterations. And let's print stopped after some number of iterations. And let's get an idea of how many times I was going around that loop. For 16, gotta wait a few seconds still. I actually went around this loop over 3 million times, right, to get to that answer. I can see that by printing out step. I can see exactly what step is, right? 1 times e to the 6th. If I reduce that epsilon, I might be able to converge quicker. Okay, certainly I converged very quickly now. But 16, that's a relatively easy value. If I go with larger values, so maybe like 511, let's say, well, I was able to get that. One of the examples from the book, I remember, was 1, 2, 3, 4, 5, 6. Please enter any real number. And I keep running this, and I think that we'll see that we run into a bit of a problem with this one. And we'll be waiting so long that I had to actually use the magic of video editing to let it complete. But we'll be iterating through this an enormous amount of times because it's just such a large number. So it's so far to the right of the number line. But what makes it particularly unappealing here is that afterwards, when it was all said and done, even with that epsilon, we were unable to find the square root. And the reason we were unable to find the square root of that value is because our step was too large. And it becomes, for example, if you try this on your own, you can see just how long this will take to actually run. I think it'd probably take hours if you decremented or decreased the step. And the only way to actually get the true answer is to decrease the step. So what we've done here is we've used a simplistic approach. It works for a lot of numbers, right? We can find the square root of 511. That's perfectly fine. But it basically starts to fall apart if we need to become extremely precise, or we're trying to find the square root of very large numbers. And that's why in the next video we'll use a better method called bisection, that instead of starting at 0 and just proceeding to the right, uses a smarter method.